Okay, so after talking about two-source interference, the last wave property that we're going to be introducing for the SL, or the core component of waves, is diffraction. And that's the apparent spreading of a wave as it goes past an obstacle or through an opening. Okay, so here you can imagine water waves, and if you had a rock in the middle of the water isn't completely blocked all the way to the shore. With it looks like the waves tend to bend around the edges and reform at a certain distance. So if you're standing here, you're kind of protected from the waves, but if you go a couple of meters away, the waves start to reform. And that's a strange phenomenon that occurs for waves, because if a wave was a basketball, like I was talking about, all the basketballs would be reflected, and only if the basketballs were here, they would go straight through. I would expect to see nothing on this side. So waves, the energy of it tends to go around obstacles. And the same thing happens when it goes through a hole. So if I had a hole in a harbor, okay, and waves are approaching, here's the wavelengths of those waves. As they enter that hole, instead of just going straight through and leaving all this area empty, the waves tend to spread out around that hole. And that's called diffraction. Okay, so diffraction tends to occur greatest, and when we talk about diffraction, the degree of it is the degree of bending around a barrier. The bending around that barrier occurs the greatest when the wavelength matches that gap size, or the size of that barrier. Okay, so if the wavelength matches the size of the barrier or the gap, which we're going to call an aperture, then I get maximum diffraction. You see here, if I increase the length of that gap, the degree of diffraction, the spreading, doesn't happen that well. Okay, so you can imagine if I had a laser, the wavelength of a laser is really, really small, and this is a door opening, the laser will go straight through. But sound, which has meters wavelength, would tend to go around. So that's why sound goes into rooms. If somebody's in the hallway, you can still hear them because the sound bends around the opening in a room. Okay, so diffraction is an interesting phenomenon where we get bending around barriers. All right. And again, yeah, maximum diffraction occurs when the wavelength is the same as the aperture. Aperture means opening size. Okay. So another interesting thing that happens when we have diffraction is we get interference patterns. Okay. And that would be when light is going through these holes. For the HL students, we're going to talk about diffraction patterns that actually happen when you have a small hole. But what we'll see in this talk, or in the core, is diffraction patterns can happen when light enters two holes and causes two diffraction patterns. And when those diffraction patterns overlap, they're going to interfere. Similar to what I showed over here in the last two-source interference lecture, if I was creating two different waves with the same pulses, those waves are going to intersect, and I'm going to create zones of constructive interference. Okay, so these are my constructive interference waves. That's where crests are going to overlap. Okay, and if I start, let's change the color here. If I start from here, and this is the second guy, all right. Remember we talked about this, the path length difference. Path length difference for constructive is on the order of a whole wavelength. Okay, that's for constructive interference. But for destructive interference, which you can also see over here, I'm going to color these in yellow. These are the dead zones that we were talking about in the two-source interference problems. Okay, so if you're standing there, you don't really see waves, and that's because, I'm going to change the color to green. Okay, that's because when they intersect here at these 2 points, okay, the path length difference is 1/2 lambda. Okay, so if it's 1/2 the wavelength, that means a crest and a trough are going to overlap, and they're going to cancel out. If it's a one whole wavelength, a crest is going to meet a crest, and they're going to add together and make a positive interference pattern. So the same thing happens here with light. When light is diffracting, okay, the two waves are going to intersect, and you can even see that. It's better to look at this diagram. Right in the middle here, the path length is always the same. So a crest is going to overlap with a crest, okay, and it makes a colored spot on a screen. okay? Beside that colored spot would be a dark area, and that dark area is exactly where a crest is overlapping with a trough. The path length difference between here and here is 1/2 of a wavelength. And you can see that they're crossing over at a half wavelength point. So all that would be dark. And then over here, we get a bright spot again because the path length difference to that bright spot is going to be a whole wavelength difference. Okay, so here there'd be no path length difference. Here it's going to be one whole wavelength difference. Okay, so that central spot that's symmetrical right in between those two holes is called the central maximum. And all these other spots that appear are an interference pattern that are going to appear by diffraction are called order, that would be my first order maximum. Okay, and then the dark area in between is going to be called my first order minimum. So a minimum meaning minimum intensity, and maximum is a region of maximum intensity. Okay, so all those numbers 1, 2, 3, 4 that you see there are just the orders of maximum intensity. And when we're thinking about that, you're thinking that, oh, that first order maximum is created by a path length difference. So a path length difference here of being one wavelength, okay? And that's how the diffraction patterns form when light goes through holes and diffracts around, okay? So the geometry of two-source interference, that's kind of what I was just talking about in that last little section, but here I just have the picture of the screen. So if I projected that diffraction pattern onto a screen, and I've done this in the classroom for you guys with the laser, you would see a bunch of dots on the wall or lines on the wall. The central one, the brightest one, is called my central maximum, and that's where the path length difference is the same between those slits. And these are all the first order maxima or minima. Okay, and this picture here is just showing you if the path length difference is on the order of a half wavelength, a crest meets with a trough, and you're going to get destructive interference. If the path length difference is one whole wavelength difference, then a crest is going to meet up with a crest, and I'm going to get constructive interference. Okay, so here I have a picture of just waves coming into those two slits. They're going to form my diffraction patterns that are going to overlap, and that part in the center is my central maximum formed by a path length difference of 0. And just again to reiterate, the other ones are formed, you can see that this second line here is longer. This line here is longer than that line. Okay, so that here would be my first order maximum with a path length difference of one whole wavelength. If it's one whole wavelength, it's constructive. Okay, and all these, every single one of these bright spots is formed by path length differences being on the order of 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, and they're all constructive. The regions in between that are dark are formed by half wavelength differences. Okay, so in the interference problems that I showed you in the last few videos, we used an equation, and this equation is derived from Young's double slit experiment with light. Okay, S is the separation between the constructive interference, the maxima. D would be the distance between the screen, and here's my screen and my two slits. Okay, the sources of the waves. Okay, in the previous videos, these were speakers. Now here is light causing diffraction being the source of the wave. Okay, little d is the distance between the 2 point sources of diffraction. Okay, and if lambda would be the wavelength. Now, we would get maximum diffraction, remember, when the wavelength is on the same size of the slits. Okay, so these little holes have to be roughly the same size as the wavelength. So if I'm going to do this experiment with light, you're not going to see those holes. They're going to be very microscopic, okay, less than a millimeter, okay, so that we can get diffraction happening from those holes. All right, so this formula here is pretty simple to derive. Okay, now it's beyond the scope of the SL curriculum. The HLs are going to have to go and derive this formula using geometry, but I'll just quickly show you, just out of interest, how this works. Okay, so I'm just going to use a yellow line here. So if I take a look at this triangle that I've generated in the middle here, okay, S and D, and that angle over there. if I draw another triangle, okay, from here to here, okay, imagine that triangle is a little bit better. Well, this length and that length, in order for that constructive interference to occur, the path length difference, okay, this area over here, that's my path length difference. So if I intersect that line, that little extra segment over here is my path length difference. You can imagine that would be the case if this is a lot farther than here. Okay, so that would approximate that. If that path length difference over here has to be equal to one whole wavelength. Okay, and so one whole wavelength is here, little d is over there. Okay, and I can draw another triangle over here, and that angle is there. Now, if this distance between the screen is like greater than 1,000 times the distance between here and here, which is usually the case, you can imagine that this green triangle is similar to that yellow triangle. Okay, so they're exactly the same. All right, so in this case, this is my hypotenuse, and this is my opposite angle. In this case, this is my opposite angle, and this is my adjacent. Okay, so I'm just going to create some identities over here. All right, so tan theta is equal to S over D. Okay, that's for the green triangle. That's for this green triangle. Okay, and for the yellow triangle, I'm going to draw that over here. For my yellow triangle, sine theta is equal to lambda, the path length difference, divided by d, okay? Now, a very important geometrical function that we use a lot in physics is that at very, 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 very small angles, sine theta is equal to tan theta, okay? So at small angles, sine theta is equal to tan theta. Okay, and in this case, the angles would be very, very small if you'd measure it on the wall. Okay, and in that case, then we get, let's just do this with the two different colors just so you can keep track. S over D is equal to lambda over little d. Okay, and then if I rearrange that equation, I get the final equation, which is S is equal to D lambda over little d. Okay, that's what we have over here. So that's how we would derive that relationship using these two triangles that we created. Okay, that's more for the HL students. They have to know how to derive this from scratch. They can ask you a question, derive Young's double slit experiment using geometry, and this would be the solution for that. But let's just quickly do a sample problem for the SLs and the HLs. How would I apply this formula? So this formula is in your data booklet, and I can apply it to, for example, measure the wavelength of a laser. So if I shine a laser at opening two slits like this, and I get this pattern on the wall, I'll be able to measure the wavelength of the laser, or I'd be able to measure the distance between the slits, okay? So I always have students, 2 or 3 every year, that do their IAs on double slit diffraction or some type of diffraction, so it's worth looking into. All right, so a laser is shined through 2 slits separated by a distance of I'm just going to erase this, separated by a distance of 0.00042 meters. A diffraction pattern is formed on a screen that is 3.8 meters away from the slits. Each bright spot is separated by 0.005 meters. Using this information, calculate the wavelength of the laser. Okay, so all right, so how can I use that information to calculate the wavelength of the laser? So again, the formula is S equals lambda d over little d, okay? And let's just make sure we plug in the numbers here. S is equal to 0.005 meters. D is 3.8 meters. Little d is 0.00042 meters. So if I want to calculate the wavelength of the laser, I need to rearrange this equation. Lambda is equal to S times D over big D. The wavelength of my laser is going to be 0.005 meters times 0.00042 meters divided by 3.8 meters. And then that would give me my wavelength of 5.5 times 10 to the minus 7 meters, which is equal to 550 nanometers, which is a green laser. Okay, those blinding green lasers are around 550 nanometers. Okay, and that's how you would apply this Young's double slit equation. Okay, now just to quickly go through an overview. The most important things for the SLs is to be able to explain what diffraction is, okay, the apparent bending of a wave around an obstacle or through an opening, okay, the spreading out, not bending, it's the spreading out of a wave, okay, and then diffraction happens greatest when the wavelength is the same size as the aperture, the whole opening. I'll get maximum angle of diffraction, all right, and then diffraction patterns are formed when I have two holes that create two different diffraction patterns that overlap. This is Young's double slit experiment. Okay, and we explained why the diffraction patterns happen because of two-source interference, which we talked about in a previous video. And that really relies on the fact that you can understand path length difference between sources of waves. The path length difference has to be on the order of a whole wavelength for constructive interference or half a wavelength for destructive interference. Okay, so we talked about the geometry. We talked about using Young's double slit equation to calculate the wavelength or the separation of dots if I know some of these variables, and for the HLs we derived how this equation comes about. Okay, it's worth practicing, and then we went through a practice problem. All right, good luck.